Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so question 10 says a group of people participated in a trial to test a new headache pill. 50% of the participants received the actual headache pill, and then 50% of the other participants received a sugar pill, right? So for whatever reason, maybe they want to actually test beyond any measurable doubt that the headache pill is actually working. So they give the other participants a pseudo pill, right? But then obviously they're made to believe that it is also a headache pill. Then, okay, 2/5 of the group receiving the headache pill were not cured. And then 3/10 of the group receiving the sugar pill were cured. Then 10.1.1 says, represent the given information on a tree diagram. Indicate on the diagram the probability associated with each branch as well as the outcomes, right? Okay, so we do understand that we have two events. So the first event having to either take the headache pill or the sugar pill, and the second event branching to either being cured or not being cured. So the way we'll represent that is, here we go. So our first event can either take the headache pill or the sugar pill. And then after taking the headache pill, you can either be cured or not cured. And then even with the sugar pill, you can be cured or not cured, right? Okay, so now there's a 50% chance of taking a headache pill or a sugar pill. Or rather, these pills have been distributed equally to the participants. So the 50%, we can write it as 50/100, and then which is 1/2. So to keep everything in fractions, then this is 1/2 and also 1/2. Now, obviously, we know following our complementary events, we know that always the branches of the tree must always add up to 1, right? So if we are writing it in decimals or fractions, when we add the 2, they must always add up to 1. If it's in percentages, we know that they must always add up to 100%. Then they say here 2/5 of the group receiving the headache pill were not cured. So not cured is here, and for not cured. So this is 2/5. Now, obviously, what number will complement this one here? It has to be 3/5. So complementary events have to add up to 1. So we are basically looking for a numerator number that when we add it to this 2 here, it will give us the same number as the denominator. So obviously, when you add them up, they have to give you 1. Then 3/10 of the group receiving the sugar pill were cured. So cured is 3/10. Now, what is the complementary event? The complementary probability of that, it is 7/10, right? So that means 7 out of 10 were not cured. Okay, so that's it with having to represent your information in a tree diagram. So just like that, you are done. If you further want to indicate that the probability is H to C, and then here it's H to N, and then here it's S to C, and then here it's S to N. You can do that. And then 10.1.2, so let's indicate this is 10.1.1. Then 10.1.2 says determine the probability that a person chosen at random from the group will not be cured. Will not be cured. So this is irrespective of whether they take the headache pill or the sugar pill. So that means we are only looking for the probability that a patient will not be cured or a participant will not be cured. Then that's not cured and then not cured. But then obviously we have to take it along with the first event. So what is the probability of not cured is whether it's probability of taking the headache pill and not cured plus the probability of taking the sugar pill and not cured, right? So headache pill and not cured, that's basically 1/2 multiplied by 2/6. 5. And then taking a sugar pill, 1/2, and then not being cured, 7/10. Right. So at this point, you just need to punch all of this into your calculator and get your solution. And then the answer that you're going to get there is 11/20. So since everything is in fractions, you can just leave it like that. Okay, so basically answering your 10.1.1 and 10.1.2 has got you 5 marks, right? So we are still fighting. We haven't won the battle. We just won a minor. We haven't won the war. We just won the battle. Yeah. Okay, so 10.2 says 3 events A, B, and C are considered. Probability of A is equal to 2/5 and probability of B is 1/4. And then probability of A or B is equals to 13/20. Now they say, are events A and B mutually exclusive? Support your answer by means of a calculation or necessary calculation. Right. So for 10.2.1, we know of a formula that goes P, A, or B is equals to P of A plus P of B minus P, A, and B. So this formula is used to test whether we have mutual exclusive events or not mutual exclusive events. But what is the determining factor here? The determining factor is the A and B. So what we know is that if we calculate our probability of A and B, the intersection, and then we find that it is 0, then we say that our events will be mutually exclusive. So that means that there is no intersection between the two events. So they are exclusive, mutually exclusive. Then, but if we calculate probability of A and B and we find a certain value that is not 0, so we can find 0.5, 0.15, or whatever value. This means that it is not mutually exclusive. Right. So if we don't get 0, it is not mutually exclusive. Right. Okay. So now having that, we can just substitute in here and try to calculate. The A or B is 13/20. And then the probability of A is 2/5. Probability of B is 1/4. So we are only left with the one that we are looking for. Then we can make this the subject of the formula by transposing it to the left-hand side. So it becomes a positive. And then we take this here, transpose it over to the right-hand side. So 2/5 plus 1/4 minus 13/20. Right. Now the probability of A and B will be equals to 0 if you punch that into your calculator. So in conclusion, what can we say? Therefore, A and B are mutually exclusive, right? Because there is no intersection between them, right? So they're mutually exclusive. So these are the ones, if you had to draw them, they would just be like this. So this would be A and this would be B, and there would be a space in between them, right? So then mutually exclusive. Okay, so now let's proceed to 10.2.2. Determine P of only C if it is further given that P of A or C is 7/20 and P of A and C is 2/5. So note that A or C means union. So the combination of event A and C, and then A and C only means the intersection, right? So where they intersect, then 2 times the probability of B and C is equivalent to the probability of A and C. So if we are interested in finding the value for this one, we already have A and C, so that means we can calculate. Let's start by that. So 2 times probability of B and C is equals to the probability of A and C, which is 2/5. Now to get rid of this 2, we can multiply by the reciprocal, 1/2. What you do on the left-hand side, you obviously have to also do on the right-hand side. Then P of B and C is equals to 1 over 5. So we know the 2 and 2 cross divide there. So we are left with the 1 over 5. You can even press Umshinwe Ibalo to confirm. Then from here now, let's try to draw and see what's going on. So looking at this, we can see that both event A and C, they are mutually connected to C. So because we can see A and C is 2 over 5, B and C is 1 over 5. But then remember, there is no intersection between A and B. So that means if we have to draw this, it will kind of look like is it Olympics or Audi? Between Olympics or Audi, there is something with this symbol. Then we have A, B, and C here. So A and B, they are mutually connected to C. But then A and B are just mutually exclusive, right? So this is a case whereby you are a friend to this one, and also this one is a friend to this one, but both of y'all are not friends, right? You have a common friend, but then you are just not friends with the other person's friend. Then, okay, so probability of A and C are we given? A and C is 2 over 5. So we can put our 2 over 5 there. And then probability of B and C is the one that we just calculated. It's 1 over 5. But there's something interesting about A here. The probability of A is the same as the intersection. So that means there is no such thing as probability of A only, because all of the probability of A is just on the intersection here. So that means we have 0, right? And then what is the probability of B? We are given 1 over 4, but then the intersection only takes 1 over 5. Guys, fractions can be really confusing. 1 over 5 is smaller than 1 over 4. So in order to get the probability of B only or only B, you'd have to obviously say 1 over 4 minus the intersection, which is 1 over 5. And then you will get 1 over 20. So you see, the fact that we can subtract 1 over 5 from 1 over 4 tells you that 1 over 4 is bigger than 1 over 5. So that means we have 1 over 20 here. Right. And then again, 1 over 20 is smaller than 1 over 5. Right. So you need your calculator when you're working with fractions. Don't just do them in your head. Then, okay. But what we are interested in here, remember, is not to calculate the probability of only B, but to determine the probability of only C. Now, how can we find that? There's one piece of information that we haven't used yet, which is probability of A or C, right? The combination or the union of event A and C. Okay, so to find the probability of only C, we do understand now that we can simply take the probability of the combination here, or the union of A and C, and then just only subtract the intersection. So minus the probability of A and C, and then also minus the probability of B and C. So you do understand that if we take all of this here, so the two circles here, and then we just subtract this, we subtract that, we obviously gonna end up with what must be in here, which is C only, right? So this is 7 over 10 minus the probability of A and C is 2 over 5 minus the B and C that we calculated, which is 1 over 5, right? So we are simply just subtracting the intersections only. Not the 1 over 20 is not part of it. And then that means having to calculate the 1 over 10, right? So I was still punching in my calculator. And then this in decimal form, we can write it as 0.1, right? Okay, now let's proceed to 10.2.3. It says determine the probability that events A, B, or C do not take place. So all the events do not take place. Okay, so if we have to bring this one back here, just realize we need the diagram also to calculate here. So the probability of no event occurring, probability of no event. Obviously, the probability of no event would mean that we have to use our complementary events. Now, everything here from the probability of the event occurring plus the probability of the event of no event must add up to what? 1, right? So it's the same thing that we've been talking about. If we are to say there's 80% chance that it will rain, that means complementary to that, there's 20% chance that it will not rain. So always your complementary events must add up to 100%, or they must add up to what? To 1. Remember, 100% over 100 is just 1, right? So if we want the probability of no event, we have to put in mind that we have to use complementary events. So if we were looking for the probability of no event, to make probability of no event the subject of the formula, obviously we'd need to say 1 minus the probability that there will be at least one event. Right. So that means probability of no event is 1 minus the probability of any event, at least any event. Then this means this is 1 minus, so that means we'd have to subtract everything. So no event would be here, right? Somewhere here. So that means no event occurring, either A, C, or B. But then now, the probability of any event occurring, that means we have to add everything that we are seeing here, including the one that we just calculated. It's 1 over 10, right? So probability of that, so that's 1 minus all of this added up. So that's obviously 0 is 0. So it's 2 over 5 plus 1 over 10 plus 1 over 5 plus 1 over 20, right? Then the value that you get from here, you have to subtract it from 1. So this, if you punch it on your machine weibalo, it gives you 1 over 4, which can be written in decimal as 0.25. So the probability that no event will occur is 1 over 5. So it's 25%. There's 25% chance that neither A, B, or C will occur. Okay, so now we are fine with that. Let's move to 10.3, your counting principles. 10.3, it says 7 friends, which are 4 boys and 3 girls, want to stand in a straight line next to each other to take a photo. In how many ways can the 3 girls stand next to each other in the photo? Right, now with this kind of questions, I will give you the long approach and also a much shorter approach, right? So let's start with the long approach so that we fully understand what's going on. Right, so I will start with this. Okay, now let's say we have this scenario here. Remember, we are trying to have these 3 girls always stand next to each other. So let's use a different color for them. So let's say this is for the girls, and then there are 3 of them, meaning that the first girl, we have 3 options, then the second girl, 2 options, and then there's the third girl, 1 option. But then if the first girl is now here, then it's the second girl, then the third girl. First girl, second girl, then third girl. First girl, second girl, then third girl. First girl, second girl, then third girl. Right. So this is how we can always ensure that the 3 girls are always standing next to each other. Now note that it can be in any random way. So it's not always that the first girl will always be here, then the second girl. So if we have to give them names, let's say there's Palisa, there's Lerado, there is Mbali, right? So it's not always that it must be Palisa, Lerado, and Mbali in that order. It can be in any particular order, right? Then with the other ones that are remaining, the other 4 friends, they can be arranged just randomly like that. So it will go 4, 3, 2, 1. And then we can just arrange the 4 other friends randomly like that, as long as they do not get to mess up with the girls here, right? So the girls must always be 3. Then the boys can be seated randomly. We can have all boys just standing like that, or we can have one boy here and three boys there, or two boys here and then two boys over there, or we can have three boys and then one boy there, or we can have all of the boys here and then the girls there, right? Okay, so now how many ways can the three girls stand next to each other in the photo? So all in all, the probability or the number of ways, so they're not looking for the probability. The number of ways is, we want to count how many blocks do we have. So in how many different combinations can you have this? It's 1, 2, 3, 4, 5. So we have 5 different combinations. But then when we are talking about in how many different ways can we arrange the girls can be arranged in 3 factorial different ways, right? So meaning that they can be arranged in 6 different ways. So 3 factorial translates to 6 ways. Now, if you want to understand it, if we have girl 1, girl 2, girl 3, we can also have in the form of girl 1, girl 3, then girl 2. Or it can be a form of girl 2, girl 1, then girl 3. And then we have also girl 2, and then we have a girl 3 here, then girl 1. And then it can be girl 3, girl 1, and then girl 2, or girl 3, girl 2, then girl 1. If you can combine, if you can just add the number of ways here, 1, 2, 3, 4, 5, 6, you will see that's 6, right? So just count the number of ways, that's 6. This means 3 factorial. Okay, nice. Now that we understand that we have 5 times 3 factorial ways, so this is for the different ways in which we can arrange the girls. And then again, what about the boys? The boys can be arranged in 4 factorial ways, randomly like that. So as you can see, 4, 3, 2, 1. Also, if you can just follow here, 4, 3, 2, 1, that gives you 4 factorial. But then there are 5 possible combinations for each of the cases. So now all we have to do is just punch all of this into our calculator, and then we get 720 ways. Now, obviously, this would be the long approach of doing that, and then for 2 marks we can all agree that that can be very, very time consuming. Right now, how would you sum up this? How would you just write it in a simplest form? Now, the best way to tackle this question would be to just realize that, okay, we do understand that we have 7 friends. 1, 2, 3, 4, 5, 6, 7. But then remember, the girls, in any case, they must always go together. They must always be seated next to each other. So that is G, 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 or standing next to each other. Then girl, girl, girl. So let's just take them as one item. Since they must always be next to each other, we can just make them an item. So that's one item. So that means in our mind, the spaces that we now have to fill are only 5, because remember, we just took this one as one item. So that means we have 1, 2, 3, 4, 5, right? So we only have 5 spaces to fill, right? So 5 standing positions. Now, if a person has to come randomly here and place them in any positions, that means the first one will have 5 options, the second one 4 options, the third one 3 options, the fourth one 2 options, and the last one only just 1 option, right? So that means we can arrange we can arrange all the learners in 5 factorial ways. But then let's not forget that we have took the girls as one item, and then the girls can also be arranged in their own 3 factorial different ways, right? So they can be arranged in 6 different ways, which is 3 factorial. So we also need to multiply that to this number here, right? So we have 5 factorial ways if we take them as one item, but we also need to remember this one item that we have taken can be arranged in 3 factorial different ways. So this is 5 factorial times 3 factorial. Then again, you get 720 ways. So now for a 2-mark question, this we can agree that it is much more time efficient and much more convenient, right? Okay. So hope that makes sense. Now let's try it in the next question, 10.3.2. Again, we will start with the longest approach. So, okay, now to do the long approach, it says in the next photo, determine the probability that Selwyn, a boy, and Lindy, a girl, will not stand next to each other, right? So we are looking for the probability that they will not stand next to each other. But knowing complementary events, we know that having this question here, it would be much easier for us to calculate the probability that they will stand next to each other. Then knowing our complementary event, we know that we can just say the probability of them not standing next to each other is 1 minus the probability of them standing next to each other, right? So having to calculate the probability of not standing next to each other, that one is a very, very difficult task, right? So now we have to be smart about it. Let's use complementary events because it is much simpler to calculate if we are to assume that they will stand next to each other. So in our approach here, we are assuming that they're standing next to each other, right? We are assuming that they're standing next to each other. Yes, we are aware that the question is saying will not stand next to each other. So let's assume that they're standing next to each other, Lindy and Selwyn, right? So this would be 2, 1, right? Because there's only two different ways in which you can place them. Can be Lindy and Selwyn or Selwyn Lindy, right? So they can decide to be seated here next to each other, or be seated in position 2 and 3 next to each other, or maybe here 2 and 1, standing, not seated. Again, I'm making that mistake. So 2, 1, then 2, 1, then 2, 1, right? So they can be standing in those positions. Now, which leaves us with how many other learners? 5 other learners, right? That we have to arrange in here. So with those ones, let's indicate them with a different color. So the other learners that are remaining, we can just place them here randomly. So in any random fashion, 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. And then also here 5, 4, 3, 2, 1. So this is just the full explanation as to how we get to that answer there. Okay, so if we are to consider how many different combinations will we have of this, it's just a matter of counting the blocks here. So we will say, okay, that's 1, 2, 3, 4, 5, 6, right? The number of rows. Then we have 6, so that means there can be 6 different combinations, and then multiply that by in how many different ways can we arrange Lindy and Selwyn. So 2 times 1 is 2 factorial, which translates to 2 ways, right? Then we can arrange Selwyn and Lindy in 2 different ways. So it can be Lindy and Selwyn, or Selwyn and Lindy, right? But then for the other students that must be placed randomly, that means in how many different ways can we arrange them? If you look at this 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, that's 5 factorial, right? So we have 5 factorial ways to arrange the other learners randomly. So we have 2 different ways to arrange Lindy and Selwyn, and then all the different combinations that we can have are 6 in total. But then remember, we are looking for what? The probability. The probability. Probability, we know that the probability of an event occurring is the number of times an event might occur over the sample space. Now, what will be our sample space? Remember, the sample space is the one without any restrictions, so no restrictions. Now, what is the possible way in which we can just randomly place the 7 friends without any restrictions whatsoever? It's when we just randomly place them like that as 7 factorial, right? So 7 friends, 7 factorial ways of placing them without any restriction. So this would this would speak to the probability of them standing next to each other. So that's 6 times 2 times 5 factorial over 7 factorial. When you punch that into your calculator, you get 2 over 7. So you don't necessarily need to find the values in here. You can just punch all of this into your calculator. But then remember, complementary event, we are not looking for the probability of Lindiwe and Selwyn standing next to each other. We are actually looking for the probability that they will not stand next to each other. So in order to get that, we can say the probability of them not standing next to each other is 1 minus any probability that they will stand next to each other. So that's how complementary events work. We are calculating the probability that they will stand next to each other and subtract it from 1 so that we erase any possibility that they might stand next to each other. And then when you punch that into your calculator, you will find your value there. It's 5 over 7, right? So you get 5 over 7, right? So that is the probability that they will not stand next to each other. And then again, obviously for a 3-mark question, that is a bit too long. So how do we solve this question in a much more convenient way and also being time efficient, right? We can just group them. So the method of grouping is the one that is effective. Right. So that is the probability that they will not stand next to each other. And then again, obviously for a 3-mark question, that is a bit too long. So how do we solve this question in a much more convenient way and also being time efficient? Right. We can just group them. So the method of grouping is the one that is effective. Right. So number 1, we assume that yes, we have 7 friends. 1, 2, 3, 4, 5, 6, 7. But then now we want to group Lindiwe and Selwyn. So Lindiwe, Selwyn, or it can be Selwyn, Lindiwe. So let's just do it like this. Or it can be Selwyn, Lindiwe, right? So, okay, these are 2 different ways in which we can place the girl and the boy. And then here, this is where we get to place the other learners randomly. So, but then if we are saying we want to take this one as one item, we want to take this as one item, because whatever we do, we must always have Lindiwe and Selwyn being together as a unit. Remember, we are still approaching it the same way. We are looking for the probability that they will stand next to each other. Then we want to have to subtract it. Right. So if we are taking this one as one item, that means how many standing positions do we now have? So if this is one item and then out of 7, that means we are only left with 6 standing positions. So 1, 2 standing positions. Right. So that means we can go 6. So for the one that will be coming here, they will have 6 options, the first one. And then the second one will have 5 options. The third one, 4 options. The fourth one, 3 option. The fifth one, 2 option. And the last one, only 1 option. So there are 6 factorial ways in which we can place these learners here. If we are to consider to make Selwyn and Lindiwe one item. But then after you have done that, you also have to remember in how many different ways can you arrange Lindiwe and Selwyn. And then from this, we can discover that there are only 2 possible ways. It can either be Lindiwe then Selwyn or Selwyn then Lindiwe. So we have to multiply that by 2. But then since this is the probability of them standing next to each other, we have to divide by the sample space, which we have already calculated. It's 7 factorial, right? Then also having to punch this in your calculator, you still get your 2 over 7. Now the probability that they will not stand next to each other is 1 minus the probability that they will stand next to each other. So this is 1 minus 2 over 7, which of course it still gives us 5 over 7, right? Which if you can just write it in decimal form is 0.71. So this would be the much more convenient way to solve it. Just group Lindewe and Selwyn, and then now you have that. But then also remember to multiply by the number of possible ways in which you can arrange the ones that you just made an item. So I hope that makes sense, guys. So with all that being said, please press the thumbs up button if you have enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.